All right, we're going to look at why all continuous time Markov chains, shorthand CTMCs, look like this. I mean the diagram below me. And I don't mean literally like that, but I do mean that all continuous time Markov chains will, over time, evolve kind of qualitatively with paths that look exactly like that picture. So before we get into continuous time Markov chains, let's revisit discrete time once more. There is going to be a state space, which is discrete as well. So this is not to be confused with what makes a discrete time Markov chains discrete. There's always going to be a discrete state space as far as we're concerned, the values that the Markov chain will take. And then there's, of course, discrete time. And once you have a state space and you've decided on these discrete time units, all you need is one-step transition probabilities to make this Markov chain come alive. These one-step transition probabilities have to be non-negative. They're probabilities, so of course they have to be non-negative. And every state x will have a distribution over the next state. So when you sum up over the next state y, you better get 1, meaning the Markov chain has to go somewhere from state x. And maybe it goes back to the state itself, so y can equal x. But that distribution for every state or the next state has to be there. And these two conditions both imply that every pxy is also less than 1, so greater than 0, less than 1, and therefore it's a probability. So in discrete time, you have a little bit of inflexibility on your hands. On one hand, if you take the unit of time to be something like a year, then going from time 2 to 3 you may kind of skip some things. A lot could happen in that 1 year, and you could be missing all sorts of things that you're trying to model that could have happened, but that you're not really picking up with that resolution. And then when you pick up, when you go to higher frequencies, say like seconds, then you kind of could be undergoing a lot of transitions that are not, they're kind of wasted. Nothing's happening and time is running, and kind of seconds go on, but nothing's changing. And so you're wasting a lot of your energy sort of transitioning. So, the answer to this is going to be continuous time. And we're going to try to motivate that with an example. I'll take one from finance. So this is a transition diagram for a Markov chain. It turns out that continuous time chains will also have transition diagrams. Here, the state space clearly is made up of A, B, AA, CC, and D. So those are all the states. And the transition diagram, of course, lists the non-zero transition probabilities. So these letters, the A, B, and CC, they refer to something. They, in fact, refer to what are called credit ratings in finance. So if you've ever rented an apartment, you would have had to provide a credit score, and the same type of a concept is used for financial institutions, but they're called credit ratings. And so if you pick, let's say, kind of a prototypical financial institution, which is maybe a bank, what happens? People deposit money into a bank, so you're in effect loaning that bank money, and one has to judge its ability to pay back those loans. So if a lot of people gather and want to withdraw money from a bank, the bank better cough up the cash, so to speak. Of course, in the meantime, when that money is sitting in the bank, those banks use it for all sorts of activities, lending, investing, all sorts of services, so on. If you're interested in banking, I would suggest you start at looking at the different types of banks that are out there. So I've listed kind of the 3 major categories. I think there are a few others, but this is sort of the kind of nuts and bolts of banking. So that's covered by commercial, retail, and investment, and all of them are subject to different rules and regulations. And if you're interested in those further, a good place to start is what's called the Glass-Steagall Act or legislation. This was passed in the 1930s after the Great Depression, and it restricted a lot of banks to only certain types of activities. And later in the 90s, it was partially or even mostly repealed, which potentially led to the Great Recession of 2008. But for our purpose, we care about the question of how do you know if you can trust a bank. So there is such a thing as FDIC insurance. So if your bank is FDIC insured and the bank goes bust, the government steps in and reimburses the depositor's money. But on a more day-to-day kind of basis, there are credit ratings by which one can judge how financially stable or worthy every bank is. So there are actual jobs on Wall Street and working for a ratings agency. I've listed 3 of the main ones here: S&P, Moody's, and Fitch. They all provide ratings. All ratings kind of have a similar sort of nomenclature to them. They kind of look like grades, like A, B, C, D. There's no F, I don't believe. But there are more kind of fine-tuned, like there's AAA, BB, CC, and so on. And kind of an intuitive way, they tell you how creditworthy or how financially kind of sound a bank, or more generally a financial institution, is. This state DD is kind of special. It stands sometimes for default, meaning inability to pay on one's financial obligations, and it is often kind of synonymous with the event of bankruptcy. So, that the bank is going bankrupt means it's going under, means it's going out of business. And so these events are often labeled banking crises when a lot of banks go bankrupt. And so I've listed some reading there in case you're interested. It's a list of banking crises from the 17th century to now. But for our purpose, we want to revisit our example and the idea. So first of all, these Markov chain models are actually used in industry. What one goes ahead is, what one does is takes kind of market data, statistical tools, and estimates a model, meaning you have to estimate the probabilities for all of these transitions there. And once you build up a model, you can all run kind of all sorts of analyses, analyze different scenarios, stress tests, and so on. I've listed one that's potentially of interest, which is the hitting time of the default state. So we're maybe interested in the distribution of how long it would take until we go bankrupt, so until we're in this state. You can see I've also added a self-transition here, meaning that once a bank goes bust, that's sort of it. And so a pretty useful thing to know would be, what is the expected time until the bank goes bankrupt, or what's the distribution of that time? It's even more informative. So those are the kind of analyses that one can run with this type of model. And one potential kind of issue with the model is sort of trying to deal with the concept of time in a discrete time setting. So there are some banks that keep or kind of maintain a really good credit rating for a long time. So this AA would be a really good credit rating. I've added a self-transition here so that you could kind of stay at that state for a long time, meaning that the bank is maintaining its this really good rating over a long period. And we're going to let P be the probability of losing that rating. So I put P here. That's the transition to the state A, so it's not as a prestigious a rating. With this self-transition and this probability P, we can model this scenario of a bank maintaining a pretty good rating. So when P is small, the bank is going to maintain the AA rating for a pretty long time. So how would we model this further? We would take a geometric random variable. We've seen these before. It has parameter P, so tau P has parameter P. And it's going to model how long the bank maintains this rating before a new grade. So it's just going to, the number of times transition here back to the state A is going to be tau P, and that's how long you stay there. And that's going to be done in some time unit. This is the distribution, as we've seen it before, the distribution of a geometric random variable. And so it's kind of like n successes or failures, you can, I guess in this case, it's a little bit more like success to stay, to maintain the AA rating, and then a failure. So you lose it on this last step here. We know that the expected time to maintain this AA rating will be 1 over P. So when P is small, we're going to maintain that rating on average for a long time. This was the tail of the distribution. And we've done a certain kind of analysis before in the case of a Poisson process, where we've let this probability of losing the rating scale with a parameter n. And so what this is doing, if you look at this quantity here, this is kind of like a time unit conversion. So say you want to go to units of years from units of seconds. Well, that's the way to do the conversion. You multiply by 1 year and divide by how many seconds there are in that year. So that's the kind of conversion that's happening. And we can, of course, take this to the limit. So we can take smaller and smaller units of time n, send n to infinity, and see what roughly the distribution, not roughly, but what exactly the distribution will be like in the limit. We've done this calculation before. It turns out that this waiting time, this geometric random variable tau, turns into an exponential one once you convert your units from a high enough frequency. And so tau p over n is roughly exponential with the rate mu. This mu comes from the definition of the probability of losing the rating. That's just a constant parameter that's assigned there. And then, of course, in the limit, tau becomes an exponential distribution. We've seen it before. This is called the survival probability. And, of course, anytime you see this, you know that tau is an exponential random variable with rate mu that appears in the exponent here. I've plotted here this survival probability. So this is a plot of probability of tau being greater than t. T is on the x-axis here. And there are a couple of kind of useful concepts to know about. One is that this probability is called the survival probability. The other one is something called the half-life. So it's actually drawn here. This plot corresponds to mu equals 1, but in general, the way to get a lifetime is to set this probability being half. So how do you, what time do you have a probability of 50-50 chance of surviving 2? And if you solve this, you get that the half-life is equal to log 2 over the rate. For a unit rate exponential random variable, the half-life is roughly 0.69. So in other words, if you have a rate of mu equals 1, then there's a 50-50 chance of making it to time 0.69. And then, of course, on average, the average lifetime is always 1 over the rate. So it would be 1 in the case of a unit rate exponential. So that's the exponential random variable. It is obviously continuous, non-negative, and we've just seen that in as far as kind of a more or less hacky way of modeling this way of maintaining a rating, once you convert once you fix a time unit and you take your discrete model and use higher and higher frequencies, you eventually get to an exponential distribution. So why not use it to begin with? In other words, we're going to take all of these self-transitions and just replace them with exponential random variables. So throw out the geometric random variables because they're associated with some particular time unit, which we don't necessarily need to kind of pick and fine-tune to. We're just going to pick an exponential and work with that. So every single state here would have an exponential random variable associated to it. It will which tells us how long we're going to maintain such and such a rating. So there's going to be an exponential random variable for the state AA, which says how long the bank will maintain the AA rating. There's going to be the same thing for the CC rating and so on and so forth. I've added one last self-transition, the only one here, which will actually be used for a very special purpose. in general, the transition diagram for a continuous time Markov chain won't have any self-transitions, with one exception. And that one exception is a state at which we stay for infinity amount of time at. So this diagram here should be read as we can stay, a continuous time Markov chain can stay at any state, but whenever you see a self-transition, it stays there for an infinite amount of time, meaning once a bank goes bust, it's bust forever. But as kind of the benefit of doing all this, we now have something very convenient to work with. We now are modeling time lengths, arbitrary time lengths, 1.43, 3.11, and so on, for every single state. And so that's the kind of nature of continuous time Markov chains. And like I already mentioned, every single state will have this exponential random variable associated with it. So tau AA maybe with rate 1/4. I'm just making up an example, which is basically saying this bank stays on average for 4 time units, and the time units are now up to you to pick. It could be maybe months, could be years, whatever you like. Tau CC for the state CC. I've here given it a rate of 2, which means we on average would stay for half, let's say a year at that rating, and so on and so forth. And then of course this self-transition indicates what's called the 0 rate. So no rate of transitioning, which translates to an infinite stay at the state. So this state is special and the self-transition is special. In general, they won't be there because in general we do want to transition from one state to another. So these absorbing states are, just because of a final note here, these absorbing states in the continuous time Markov chain setting are the only ones that are going to have a self-transition. Otherwise you won't have them. You'll just model the length of stay by an exponential random variable. And so every single continuous time Markov chain, like I mentioned, will look like this. So let's discuss this picture before moving on to the next clip. So first of all, there are 2 ingredients that go into a continuous time Markov chain. One is a discrete time Markov chain that has essentially no self-transitions, with that exception that I mentioned, in infinite length of stay. And the second thing, it will have a rate for every single state assigned that is going to be used to generate a waiting time, so how long we stay in that state. And so here the diagram is listing the states on the y-axis here. So the states are, in this example, z, u, v, x, y, and these time intervals here are how long we wait at each state. So we wait for t1 minus t0 time at state x, t2 minus t1 at state y, and so on and so forth. And so this is exactly what in continuous time every single continuous time Markov chain will look like.